I'm Ryan Moran. I'm on the steering committee for Paketo Buildpacks. I am also an engineer at VMware.
Hello, my name is Sophie Wigmore. I'm a member of technical staff at VMware and also a maintainer on the Paketo Buildpacks project.
And this is what's new with Paketo Buildpacks. Just to start off, Paketo Buildpacks is a project under the Cloud Foundry Foundation. You may have seen some of our stuff earlier in some of the talks. It was in the Karifi talk, actually building out the Java application they had there. We have a plethora of new build packs that we've built over the last couple of years. And we're looking into, Greg hinted at, we're looking into bringing those things into Cloud Foundry proper in the future. But if you want to go try out Paketo Buildpacks, they work today. You can try them out with Kpack. You can try them out with Pack, just building Docker images yourself and then run them anywhere that a Docker image might run. So with that background, we'll take a look at what are build packs.
Yeah, just to get started, little 101. So we're talking about Cloud Native Buildpacks today, not the V2 build packs that were in Cloud Foundry before. And build packs are an implementation, well, the Paketo build packs are an implementation of the upstream Cloud Native Buildpacks project, and they provide you a way with containerizing your applications. So if you have an application written in one of the languages listed up here, likely you have a Docker file to containerize that application, and you have to maintain that. Well, when you want to use build packs, all you have to do is provide your application source code. Once you have your application source code, you'll need to select a platform of choice. As Ryan mentioned, you can use the Pack CLI, which is provided by the upstream Cloud Native Buildpacks project, and there's also Kpack as an option, and the platform is going to be your integration point to using the build packs. Once you have your platform, then you need to specify what type of build packs you want to use. There are many different implementations of Cloud Native Buildpacks out there. And so if you want to use Paketo Buildpacks, probably the simplest way to specify that is to use a Paketo builder. And builders are just comprised of Paketo Buildpacks and a Paketo stack. So we have Paketo Buildpacks for all the different language ecosystems that we have listed up here. And also we have a set of Paketo stacks. And stacks are just the base operating system that your application is going to run on in the final application image, and also the base operating system for the actual build. And the stacks also include a number of different OS level packages that we provide. So that's what's inside of a builder. So once you decide that you want to use Paketo Buildpacks, you specify a builder to use with the Pack CLI and start your build. And you'll get a bunch of logs, as you'll see in a demo later on, of what's going on with your build. So the final app image is OCI compliant and production ready, and it contains a number of different layers. There's a base operating system layer, application layers for your actual running application, and then there are application dependency layers. So any dependencies that were installed during the build will exist in those layers. Just to really drive it home, if you were using a Docker file to containerize a very simple Python application, we'll just show how that kind of translates to a build pack steps that it would do during a build. So the first thing that you usually find in a Docker file is this from line, where you're specifying the base OS image. So if in this example we have the Paketo Buildpacks Jammy base image, and that is the equivalent of just using the Jammy base stack. Next, if you were containerizing a Python app, you would probably want to install Python onto your image. So here you have like a curl step, and you would want to install a specific version and then add that to your Python path or some path so that you can access it. And that is what the CPython build pack would do, and that would be automatically detected. Your app would automatically be detected as a Python app by the build packs. And you get the added benefit that the CPython build pack and our other build packs, for that matter, can determine what version to install. So you don't even have to specify that if you don't want to. Then the next step you might want to do is to run pip install or run some kind of package manager to install your application dependencies, and that is what the pip install build pack would do in this example. And again, we have the added benefit of layer caching, so any dependencies that get installed during the pip install phase would be cached for reuse on a rebuild.
Before we move on from this, one of the things you'll probably notice is there are 3 different build packs on this page. The build packs in CNB are considerably more modular. They're designed to be broken apart and pieced back together to solve different types of problems. This is a big difference between how Paketo Buildpacks and CNBs operate today versus how the old school V2B build packs work inside Cloud Foundry. Gone are the days of having to fork and then perpetually maintain a customized version of a build pack for your specific use case. Instead, you can take one of these individual steps, swap it out with something that you actually want more specifically, and you maintain just that tiny little sliver. The rest of it stays up to date, and you can stay on the main line.
Good point. Yep, and the final step is actually running your app. So running python server.py, and that is done by the Python start build pack. So hopefully that gives you a little bit of insight into what a build is kind of doing under the hood.
So, given that background, what's new in Paketo Buildpacks? There's a lot of stuff we've worked on in the last year. Some of the highlights were things like support for JavaScript front-end applications, improving our kind of story around reproducible builds, improving stack creation tooling. This is a big one for folks who are running on top of Ubuntu, which is pretty much everyone in the Cloud Foundry space. You may have noticed that this last year, Ubuntu released a new 22.04 release that is completely new LTS release for Ubuntu's operating system. For us, that meant updating all the stacks. It meant updating all the build packs to run on top of that stack. And we made some pretty big improvements to our stack creation tooling around this. The upshot of that is for in the future, if we wanted to add things like UBI support or support for smaller images like Alpine, we could go ahead and do that much more quickly than we have been able to do in the past. I said already Jamie stacks and build pack support. We also have completed our entire SBOM support across the entire project. And then very recently, we introduced remote debugging support for .NET Core, which we'll talk about here in a second. So let's talk about one of those features, and that is the support for JavaScript front-end applications. If you're familiar on the Cloud Foundry side with the static file build pack, then parts of this might seem pretty familiar. The use case here, for the most part, is say you have a React or a Next.js application that you want to run that's running in your, in the client's browser, and you're going to want to serve that from your server. So you're talking about some bundle, some payload of CSS or JavaScript, and a web server like Nginx or HTTPD. Historically, what we've had you do is go ahead and bundle up all those assets and then include that next to the static file declaration, and you'd push that on Cloud Foundry. What the web server's build pack is giving you is we're going to handle all of it directly from source. So we're going to take your source code, and we're going to see that it's a JavaScript front-end application. We're going to install Node. We're going to install all the dependencies. We're going to then run the build step to turn that set of dependencies in your source code into like a minified gzipped bundle that then can be served by a web server. We'll install a web server, and we'll have that then be able to serve all the traffic that's requesting the JavaScript front end. The cool thing about this is we've gotten rid of the static file entirely. So you're going to be able to do this with declaring 2 environment variables. You basically say, this is a front-end JavaScript application, and I want you to serve it with Nginx. Everything else is configured for you in a default configuration. There's obviously some modifications you can make to that. And if you want to bring your own Nginx config file, you can do that as well. So let's take a look at a quick demo. Here, I have a simple React front-end application. You can see here in my source directory, I've got an app.js file. And if I go ahead and cat that, then you can see here, I'm just serving some React code. Specifically, this is just what you get when you do create React app. And then here in a second, so now I'm going to, This is annoying. I'm pack building my application. So let me talk through some of the steps here, because this is probably the first time you're actually taking a really good look at what's happening here. So you can see in my command there, I've said pack build my web app. That's the name of my application. I have then specified the build pack I want to use. I'm using the web service build pack. It's going to do a few things. It's pulling down a builder. That's the thing Sophie talked about earlier. It's pulling down the build pack that I want to use. It's pulling down the run image and the build image. These two images are different. They're basically, the build image is going to have all sorts of stuff that you might want during the build phase, and the run image is a slimmed down version of that thing that you might want to have, reducing the set of dependencies that are available at runtime. I'll pause here for a second and talk a little bit about what's happening here. So you can see there at the top that it says that it's installing this version of Node and that it's configuring it for production. You can also see that it's setting up a bunch of stuff that has to do with optimizing memory inside the container. This is important for folks running stuff on Kubernetes and not wanting to hit the killer for their pods that they're running. And then you can see here that it's going ahead and doing an npm install. So it's going to automatically detect all of the packages that you have specified for that React front-end app, and it's going to install them. And in this case, it's doing an npm CI. The actual npm install build pack is capable of figuring out what kind of JavaScript package manager you're using. So we have support for Yarn and npm. And then within npm itself, we can see like, oh, you checked in a package lock. We're going to make sure that we only install specifically those dependencies that are declared in the lock file. And then we can see here that it's generated an SBOM. Sophie will talk a little bit more about SBOMs in a moment. But the cool thing is that when the image is actually built to completion, you'll be able to look and see all of the actual dependencies that were used even during build time, not just the stuff that ends up in the final run image. And now that that's completed, we're going to go ahead and actually build the React application. So we're running this npm run build command, and that's just basically taking all of your source code, all of those dependencies, and smishing them together into this minified gzip bundle. And the very last bit is just installing Nginx and configuring it, and then setting the start command. So the last thing I have is I have well, that skipped through, but basically I'm just Docker running the image that I had, and then you can see there in the browser that it's actually serving my JavaScript application. All right, so then there's stack tooling. Stack tooling is another area we've made a huge leap forward in this year. Prior to this, all the stack tooling we had was basically the stack tooling that came from the Cloud Foundry community. So earlier when Greg was talking about the addition of CF Linux FS4 to Cloud Foundry more generally, the ways that those images were built on that front was basically the same way that Paketo was building its base stack to begin with. And what we've done instead is we've gone through the process of figuring out a declarative way of specifying what actually should go into a stack. So we have basically a giant TOML file that says this is the base image declaratively, and here are all the packages that I want installed in that specific file. It will then go out and install the correct set of packages for the build image, install the correct set of packages for the run image, and then and it will do this all with support for multiple architectures. So for us, the thing we continue to hear about from folks is they want ARM64 support. Our stack tooling has support for this. It's coming in the future. We don't have it yet today, but for those of you that are running on top of like M1 or M2 Max, we will have native support for you in Docker image for Buildpacks at some point in the future. The other cool thing is that you can use our tooling off the shelf. You can take it and you can use it to build an Alpine-derived stack or one that's built on top of some new exotic stack like Wolfie. But let's take a moment to talk about what a stack is. I mentioned this earlier. There's two parts to it. There's a build image and the run image. Both of them have a base operating system. So for us, within the Paketo project, we're just talking about Ubuntu. Historically, we've had support for Bionic, and then since April, we've had support for Jammy. On top of that, the build image and run image have a set of packages that they install. The build images packages lean towards those that you would want available when you're actually compiling and building your application. So this probably includes stuff you don't want in your run image, like GCC. And then the run image is a slimmed down set of those dependencies, ones that you actually want to be available at runtime, but are only there to make your application run and don't become attack vectors or security vulnerability issues going forward.
Cool. So I am going to show a quick demo of that stack creation process that Ryan was talking about. And before we start, we are going to be showing an example of what we do for the Jammy Tiny stack. So it's the Jammy variant of our stacks that has the least packages, minimal amount. And I was going to say something else, totally blank, so we can just get started. Okay, so just starting off, this is the directory, but all you're going to actually need to create your own stack is what's inside of the stack directory here. So the main things to point out here are the stack toml file, the run Docker file, and the build Docker file. And all of these files conform to an RFC that was laid out in the Paketo project for what these should look like. So the stack toml is a set of different fields that we'll look at in a second, and they are already laid out for you, so there's no guessing on what that should contain. So looking at the stack.toml file, we see that there is a section for build, and it contains a reference to the Docker file that we're going to use, the user ID, the group ID, the shell that will be running on the image, and the sources that we want to grab packages from. Down here, you can see all the packages that we're going to be installing on the build image. And then down here, we have the same thing for the run image. And as you can see, there is a slimmed down set of packages here. Then if we just take a quick look at one of the Docker files, we see that we have that front statement referencing the Ubuntu Jammy base image that we're going to be using. And then we have a bunch of different commands to install packages, set up labels, and then do some cleanup. We can use the jam tool, which is the tool that we have that you can use to create your own stacks, and we also use it to create our stacks, our build packs, and keep them up to date. So as you can see, there's a whole bunch of different functionality that you can use here, and we'll just take a look at create stack. So we're going to pass in the build output, the run output, and the config file. And we've sped this up a little bit, but this is all you need to do to create your own stack, and it will spit out some logs while it's doing the build. As you can see, it's pulling in the base image, it's installing some packages, adding different environment variables and labels, decorating the images. And these images, or these OCI archives, have been exported to the directory that we specified, and we see them right here. So those are OCI tar archives, and we can use Scopio to copy them onto our local Docker daemon. You can also push them up to a registry. So now if we take a look at our Docker daemon, we can see that both of those images are present here. And we can just close this out by looking inside of one of those images. We can look at the build image, and we can look at the OS release file and see that it has content related to Jammy. So that's the base operating system that's being used here. Cool, so that's the stack creation tooling that we've added in Paketo. Next up, the next big feature is SBOM Support, and we just released that in Paketo Buildpacks across all of our language families, and it's a big deal because SBOMs are really important right now for secure software supply chains and getting insights into everything in your application's tool chain. we, under the hood, use Incore's SIFT library to generate the SBOMs during the build, so you can get access to the build time dependencies that you might not get if you were just scanning your source code or your final app image. And we support CycloneDX, SPDX, and SIFT schemas, which if you know anything about the SBOM, hopefully one of these schemas you've heard of and might be useful for one of your use cases. So we'll show a quick demo of what this looks like when you use Paketo Buildpacks and when you want to look at the SBOM that gets output. So in this example, we'll be showing you a really simple Python app that uses Poetry as its package manager. So as you can see here, we have the app, and there is a Poetry lock file containing dependencies that we'll want to install during the build, server.py file, and an index.html. We can take a quick look at the Poetry lock. We see that there are a bunch of different packages that we will hopefully get SBOM entries for, and we can do the pack build. And just one thing to call out in this command, it's very similar to the one Ryan just showed. We're using the Paketo Buildpacks Python build pack. We're calling that out specifically so it's clear in the example, but more importantly, you can also see that we're specifying an SBOM output directory, and that tells the pack CLI where you want the SBOMs to be output in, because they are stored on the application images or on the images as we build them. So if you want to export those, you'll have to specify that field. So as the build runs, you can see the same logs as before. We're installing different things depending on the app, but specifically you can see that we're generating the SBOM for different parts of the build. So in this example, we're generating the SBOM for the CPython dependency that was just installed by the CPython build pack. Same again for the pip dependency that we install, which is needed for Poetry. And again, for the Poetry dependency that we install, and I think the logs got cut off, but we do the same thing for all of the Poetry dependencies that we install when we run the Poetry command. So we have the Poetry sample app image, and we see that there's this SBOM content directory with a nested directory structure for each of the different build packs that just contributed, and anything that got installed on the app image has an SBOM entry here. And you can see that they're separated by build, cache, and launch depending on when that dependency is available. So if it was just available during build, it will be found in the build section, and if it was just available on the final app image, it will be available in the launch image or the launch section. So we can look at specific entries inside of here. Looking at just the Poetry installed dependencies, we can take a look at that. And just running a JQ command on it, we see it's a giant block of JSON, which is what you might expect for an SBOM document. But looking inside, we can see that there are specific entries for some of those Python packages that we looked at earlier. You can see the type listed here is Python, and we have lots of different metadata like CPEs for vulnerability scanning, versions, checksums. Some of the packages have licenses in some languages, but right now in SIFT, I believe that Python license information is not available, but depending on your language, that would be there. And there's tons of different information about all of your packages. And you'll notice, well, we won't go too much more into this specific document because JSON isn't that fun to look at, but this specific document only contains entries for the Poetry installed packages. That's because we keep each of our SBOM entries separate for each of the individual parts of the build. We can then use Gripe, which is Incore's vulnerability scanner, just to scan our SBOMs. That's just an example use case that you might want for the SBOMs. And here, when we scan the Poetry SBOM document, you see that there are no vulnerabilities found. But that might not be the case depending on what versions your application pulled in. So if we scan a different SBOM, maybe looking at the one for the pip dependency itself, we can also scan that. And it just so happens that the version of pip that was installed during the build has a high severity vulnerability. So that's kind of a good example of why you want all of the build time SBOM information, so you can get access to all of that information in one place. Oops. Okay, so we have barely scratched the surface of the Paketo Buildpacks SBOM offering. So some selfish self-promotion. We have another talk on Friday about the Paketo SBOM experience and all of our learnings that we've encountered trying to implement this. So if you're interested, definitely come by on Friday, and the QR code for our talk is up there. And while we're promoting other talks for Paketo Buildpacks, up next we also have my colleague Tim doing a lightning talk on .NET Core remote debugging support with Visual Studio Code. So definitely stick around for that if you're interested.
So a little bit about the community. We've got a lot of contributions in the last year, somewhere around 2,500 pull requests from 71 different contributors across 160 repositories. That kind of, when I gathered that information, it kind of astounded me. The VMware contributors that I work with every single day, there's about 8 of us. And so it was really astounding to see a number like 71, meaning that there are a lot of other folks out there who are interested in contributing to Paketo Buildpacks and have done so successfully. So if you're interested in doing exactly that, we invite you to. We're an open community. We hold open working group meetings every week. And we have an open governance process and an RFC decision-making process. And so yeah, we'd love to see you at one of our working group sessions or engaging us on Slack or through our mailing list. In addition to those pull requests, we saw 859 issues from 148 submitters, and that's covering 132 of our repositories. So yeah, even more folks who are probably using our build packs, finding bugs, reporting them, requesting new features. It's really great to see people engage from the community and give us feedback about what we're building, give us insights into the type of applications they're trying to deploy, and just give us good ideas for things that would be helpful for other folks. In addition to that, we keep track of folks who actually use Paketo Buildpacks in their products or using them at their companies. Some of the recent additions to our adopters list include the companies that you see here: Bloomberg, Doximity, Randoli, Greenhouse, and Knative. If you're interested, I don't think we have a code for this, but Knative is giving a talk later this week at some point where they do talk about their use of Buildpacks, specifically Buildpacks that allow you to use functions on the Knative platform. Those are built on top of the Paketo Buildpacks themselves. So if you're interested in that kind of platform integration, it's worth a look. And so to bring it home, if you want to get in touch with us, you can reach out on GitHub, or you can check out our website, paketo.io, for documentation or to just figure out what is there in the Buildpack space. Or you can reach out to us directly on Slack. We love to hear feedback, questions, comments, concerns, any of those things. And with that, thank you. Any questions? Thank you.
Wow. Do you know of any tools that are available for converting V2 Cloud Foundry apps over into Paketo Buildpacks?
I know of something that maybe with some modification might be able to do that. I don't know of anything specifically that does exactly that. Heroku, when they first launched their support in the CNB space, they didn't want to go through the work of having to port every single one of their Heroku build packs over to something that ran on top of CNB. So they wrote a CNB shim tool that basically takes their V2 build packs and wraps them in a wrapper that's capable of running on top of CNB. Now, Cloud Foundry build packs are slightly different than that. And so you might have to modify a couple of small places, mostly to get kind of the outlier features. But if you're running kind of the mainline stock basic versions of Buildpacks, then I would bet you could run their tool and get something that could work.
Awesome, thank you. Just quick follow-up question. Do you know if CF deployment is going to keep supporting the V2 style, or is there an end of life anywhere on the radar for those?
I would defer to someone on the, like Greg or someone who's running on the app deployments side of things to make that decision.
Great, thank you.
Yeah, there's currently no plans to get rid of the existing V2 build packs, but it is something that could conceivably happen in what I would call the distant future. But no plans right now.
Similar question to one just now, but from Joseph Palermo remotely. Is there a plan to bring full Cloud Native Buildpack support to CF? Greg mentioned earlier a new effort to wrap the CNBs, but it seems like CF is missing out on a lot of the CNB value.
Yeah, again, I don't want to make the decision for another team. If we were to go the route of, I mean, I can talk hypothetically about what that kind of thing might look like and why I shouldn't be the one to make the decision. But the majority of the work for enabling that type of functionality would have to be stuff that exists in Cappy and Diego. So it would most likely be those teams that would have to make the decision about supporting Cloud Native Buildpacks natively. And so because we're just building the build packs that would run on top of that infrastructure, we're not necessarily well positioned to say like, yeah, that's going to happen. We would happily support it if it did, but yeah, I'm not gonna put it on those teams to make a decision for them.
Right. Thank you.